repeat what you just said to me.
Out loud, or are you typing?
Yeah, out loud.
Multiply the power it's raised by to the coefficient and subtract 1 from the power. Any constant, get rid of.
Okay, very good. That's pretty much it. Okay, so to find the derivative of this function, what Brandon had said is multiply the coefficient by the power. So in this case, we're going to multiply it by, that's 12x to the third power plus 4x here. Now, one thing I probably was not mentioned was, what did we do with the original powers? What did we reduce it by? Reduced by
1.
1. Thank you. So let's also remember that, okay? So yeah, so Brandon also wrote it right here. I may have not heard that, so sorry about it, but I'm having it up right here on my screen. So there you go. I didn't have a constant here, but let's say if it was adding 3 at the end of it, obviously this would go to 0. Okay, so that's it. That's how you would tell somebody how to find the derivative of a polynomial function. So if we were to try to describe the antiderivative, then the main definition is it's the opposite of the operations you did for the derivative. So if we multiply the coefficient by the power, the new coefficient now has to be divided by the power. So we're going to go take f prime of x and go to f of x. Okay, so here I'm going to take 12 divided by, I don't know which one it is yet, but I know that it was 3 earlier. I'm going to add 1, so I'm going to do 12 divided by 4 plus 4 divided by 2 x to the 1 plus 1. So what does that give me when I clean this up? 3x to the 4th power plus 2x squared. Okay. Now Brandon brought up a very good point. Any constants get rid of when he was talking about the very first explanation of the question. Here, let's say I was given the f prime instead of f. Okay. So f prime, if you were to cover f, all you had was f prime. You wouldn't know what that constant was before. It could be 3, it could be minus 10, it could be plus 20 over the natural log of 8. We don't know. So what do we write? Plus c. So Brandon, you brought that up. You brought up a very good point. Actually, that wasn't obviously you probably didn't know, but actually you wrote the word constant. I'm going to write that back. I'm going to use what you said and say I'm going to write constant when I go backward because I don't know what that constant was. Okay. So this is my original function. This is what it looks like, because no matter what constant I have here, if I take the derivative of this equation, I will end up with f prime. So that pretty much sums up a lot of what we're talking about, what we're going to begin talking about today, and the examples we're going to do for right now. So let me make this a little bit smaller so I can move this up. No, I don't want to do that. I don't want to do that. Okay, so now we're going to take a look at this one here. Find each of the following antiderivatives. Okay, so the first one should not be too hard. Now, first thing I want to go over with you guys is that the antiderivative expression looks like this. Okay, this is what we're going to start off with. If x is our variable, we write the integral of the function. Forgot to put f right there, dx. Okay, if it's f of s, then it's the derivative of the antiderivative ds, okay, for example. So this is my expression. And it says right here, the antiderivative of a function f of x is denoted by this. These are written up here for you, okay? So here, this is telling me to find the antiderivative of 3x squared plus 2x plus 3. So if I do this expression, instead of subtracting the exponent by 1, we're adding it. So x to the 2 plus 1. Instead of multiplying 3, the coefficient, by the exponent, we're going to divide by the new exponent. Same thing with the next one. 2x1 plus 1 divided by 2, then plus 3. Now this had a 3 here. The f of x function now is 3x. And so this is what it looks like operation-wise. And now I'm going to go ahead and clean it up. So this is f of x equal to just 1x to the third power plus 1x squared plus 3x. Now, again, I most likely had a constant here. I don't know. But whatever it is, I don't know what that constant is and it's not defined. So I had to write down plus c. That plus c talks about all constants that exist, okay? So this is my original function as we see it. Now the next one here, I see this, and I said this in the earlier class, I think to myself, hey, when I took derivatives and I saw a function like this, I always think to myself, oh boy, think of quotient rule or whatever. Well, remember, the first thing we want to do is always simplify as much as possible. So there isn't really a quotient rule for integrals. We'll get to that more advanced stage later. But instead, what we can do is we can divide each of the monomial terms by x. So we can rewrite it as x to the third divided by x is x squared plus 2x divided by x is just 2 minus 4 over x dx. Okay. So let's practice again. I'm going to change x squared to what power? X to what power, guys?
The third power?
That's correct. So just remember what I did over here, right? I'm going to write it in red. See, I did this over here. I added everything by 1. So x to the third power. Now, there's a 1 here, right? So 1 divided by what? What exponent? 2 or 3?
3.
Correct. So always divide by the new exponent, okay? Plus 2 times x, obviously the 1 power. So just to be consistent, 2 divided by 1. Again, this is writing f of x. So now the next one here, I'm going to rewrite this a little bit. If I do this, I can separate the 4 outside of the integral, because I'm basically taking the integral of each one of these, or the antiderivative. If I were to rewrite this, just focusing on this part, I can write it as 4 to the x to the minus 1 power. Now, we all know that what we're doing here is adding 1 to the exponent every single time. If I add 1 to this guy right here, I'm going to end up with 0. So to show that, I'm going to end up with this 4x to the 0 power, and you have to divide this by 0, right? Because that's what we did over here every single time. Well, this is going to end up with something called obviously undefined because that doesn't make any sense. And if I were just to look at x to the 0 power, x to the 0 power will become 1, right? Because anything raised to the 0 power is itself unity. So then I think to myself, okay, there's an issue here with what I have. I can't take the antiderivative as I normally did with these guys. So does anyone remember what the derivative of the natural log of x gave me? This is kind of like going back to a little while back. We didn't do too much with it, but it was like one of those special derivatives. Does anyone remember? And you can probably search it on the computer right now. What is the derivative of the natural log of x?
Is it 1 over x or no?
No, you're correct. Thank you, Veronica. It's 1 over x. Remember that the derivative of natural log of x was, I wrote the original function on the bottom, and I took the derivative of it on the top, right? So, for example, if it was derivative of natural log of, let's say, x squared minus 1, for example, then this would read as 2x over x squared minus 1. So that's why you notice there's a 1 on top, because the derivative of x is 1. And if we take a look at the graph of the derivative of this function, it looks like 1 over x. So if the derivative of natural log of x is 1 over x, and then the antiderivative is the opposite. So I go from here, and I'm going to go back to what? What am I going to end up with if I take the antiderivative of 1 over x? Where am I heading to?
You'd be heading back to natural log of x.
Thank you very much. So this part right here, the antiderivative of 1 over x dx is the natural log of x. So remember that what we're doing is that we're actually doing reverse operations, right? So if the derivative of natural log of x is 1 over x, then the antiderivative of 1 over x is what? Natural log of x. So clearly, what we have is this function rewritten as 1/3 x to the 3rd power plus 2x minus 4 times the natural log of x. Sorry, it's a little crappy there. Then I'm going to write plus c because there's probably, we don't know, but there might be a constant that existed before. And that's my answer. How are we doing so far? Does that make sense? Okay, so I'm going to go ahead. Take this and move it up. And now you have these two. I'm not going to go through these too much because now they're just repeats of each other, of problems before. What I do want to go through is simplification. How do we rewrite functions to make it easier for us? This function has been FOILed apart. What should I do in this situation? Should I multiply it back together or should I keep it like this? Multiply, very good. So if I multiply this, this is 2x squared plus x minus 6 dx. Very good. This one here, I can rewrite this. Remember, radicals, there's nothing we can do with radicals, but we can rewrite them in exponent form. So this is x to the 1/2, so the bottom. So I'm not going to do this one because this is basically like the one above, but I am going to work a little bit with this one with you guys before we end the class. I can rewrite it one more time as 2 times x. This is ugly. 2 times x to the negative 1/2 dx. Now, we're going to do the exact same thing. We're going to add 1 to the exponent when we take the derivative, and then divide the coefficient by the new exponent. So what do I get when I add 1 to negative 1/2?
X to the power of 1/2.
That's correct, a positive 1/2. Now I got to take that coefficient and divide by 1/2, but that looks kind of strange, right? Like a whole number divided by a fraction. So instead, this is what f of x is going to look like. So instead, when I divide by a fraction, I can instead multiply it by its reciprocal. So this would be 2 over 1 times 2 x to the 1/2. And then I'm going to write at the end plus c. So if I clean this up a little bit, what does my final answer look like? What does my final answer look like before we go? Oh, okay. Thank you, Isa. 4 times x to the 1/2 plus c. That's correct. And there you go. So now we have just begun our first practice with antiderivatives. We're taking the f prime function and going back to the f function. And what we're doing is that we have to just reverse order or operation everything we've done with derivatives. Okay? Remember, we're always going to add the exponent by 1. And then we're going to divide the coefficient by the new exponent. So if it was x to the 3rd power, it becomes x to the 4th, and then we're going to divide the coefficient by 4. Okay? And at the end, always write a plus c, because we do not know what specific function it had before. It could have been plus 2, it could have been minus 2. It could have been plus e to the x, or e to the 2nd power, or minus e to the 2nd power. You know, it could be anything. We don't know. So the constant letter or variable I write here is encompassing all constant numbers that are possible as a solution. Is the dx something we carry down, or do we leave? No, the dx is gone because the integration, dx meant the derivative, right? Because we differentiate the function. The antiderivative basically took care of that. Okay, so what we're showing here is what are we actually differentiating this function for? Therefore, we know what we're taking the antiderivative of. All right, So I'm going to go ahead and stop share here. And I'm going to stop recording.